Okay, let's finish up chapter 1. We're going to go back to section 1.5. It's called continuity. So we'll start out with the definition of continuity, and we're going to be looking at the definition at a point. So this is, what does it mean to be continuous at a point? A function f is said to be continuous at x equals a at some point if the limit as x approaches a of f of x equals f of a. So what does this mean? Let's see. So when we look at this equation, this has to be true in order to say the function is continuous at a. It means, first of all, the left side of the equation means that the limit exists. So the limit from the left and the right, because there's no negative or positive sign here, that means this limit right here exists. The function is approaching some value from both the left and the right. The right-hand side of the equation means that the function is actually defined at a. So we can't have a function undefined. The function must be defined at a, and whatever the value of the function is at a must be equal to the limit. So wherever the function is heading to, as we get closer to a, must be equal to what the function is defined to be at a. All right, let's look at a graph just to try and understand what's happening here. Is this function continuous at x equals 2? So here's 2. As we approach from the left, we're approaching 8. As we approach from the right, we go up and then we come back down and we're also approaching 8. So the limit exists. The limit as x approaches 2 is 8. The problem is at 2, the function is undefined. So here's what we'd have. The limit as x approaches 2 of this function is 8, but f of 2 is undefined. So it's not continuous there because f of 2 is not defined. So we have to have this not be an open hole. It's got to be filled in order for it to be continuous. Look at this one. Here, again, the limit from the left is 8. The limit from the right is also 8. At 2, though, the function is defined, but it's defined to be 6. And what we need is for the limit to be equal to the function's value. So even though the limit exists and it's equal to a, and even though the function is defined to be 6, that limit and the value of the function, the 8 and the 6, are not the same. So our function is headed towards something from both sides, but it's not headed to what it needs to be headed to, which would be 6 here. So this would not be continuous at 2. Now here, this example satisfies everything we need. As we come in from the left, it's headed towards 8. As we come in from the right, it's headed towards 8. And the function's value at 2 is 8. So we have the limit exists and it's 8. The function is defined at 2 and it's 8. Since these two are equal, the function is continuous there. So the meaning. So the basic idea here is that to be continuous at a point means that we could draw the function with the pencil through the point without picking up our pencil, without lifting it. It's continuous. So when I draw this, if I were to start drawing this and I head towards 2, I just keep drawing right through it and I'm good. I never have to pick up my pencil. Where with this one, in order to draw this function, I would have to draw it, then I have to pick up my pencil, draw this dot, and then come back and continue. So it was not a continuous motion through there. It had a little jump here. I had to pick up my pencil. Same with this one. To draw this one, I'd have to draw, and then at some point I have to pick up my pencil, jump over that point, and then continue to draw it. So it would not be continuous. So, discontinuities at a point. If a function is not continuous at a point, x equals a, then we say it is discontinuous at a. So that's just a general, it's kind of the opposite of continuities, or being continuous would be to be discontinuous. Now there are some certain types of discontinuities, places that we would have our function not be continuous. The 3 basic types are jump discontinuities, infinite discontinuities, and removable discontinuities. So let's look at, first of all, a jump discontinuity. This function has a discontinuity at x equals 2 because as I draw it, at some point I have to jump and continue to draw. So this break in the graph makes it not continuous. So we call it a jump discontinuity. And again, you can look at the limit from the left is 8. The limit from the right is 5. Automatically, we would say it's discontinuous because remember, for continuity, you need at least the limit to exist. Here, the limit doesn't even exist. The other type of continuity, or the second type, is called an infinite discontinuity. So notice with this one, as I come into 2 from the left, I'm headed to infinity. Come into 2 from the right, I'm headed to infinity. So the limit exists because they're both headed towards positive infinity. But the function's value at 2 is 5. And we need those to be equal, right? We need the limit, which is infinity, to be equal to the function's value at 2, which is 5. Obviously, infinity is not equal to 5. So this would be discontinuous at 2. We call this an infinite discontinuity because one of the sides is headed towards some infinity, either positive or negative. The last type of discontinuity is what we call a removable discontinuity. So this was one that we saw earlier. I'm trying to draw this. I have to pick up my pencil, then I can continue. At 2, the function is undefined. That's what causes it to be discontinuous. So we know the limit as we approach 2 is 8. So from both sides, it's 8. The function's not defined at 2, so that's what makes it discontinuous. We call it removable because it would be very easy for us to remove this discontinuity, to make it continuous. All we would have to do is fill that hole in with the value of 8. So we just needed to define the function to be 8 at 2. If we did that, then we would remove this discontinuity. Here we can't remove this discontinuity. There's nothing we can do. We can't define the function at 2 to be infinity. That doesn't make sense. No function can be infinity at any point. So we can't remove that discontinuity. And same with this one. There's no way that we can paste these two graphs together to make them both, come in from the left and the right together. We'd have to change the function completely. It wouldn't be as easy as this one, which is just filling in that point. I hope that makes sense. All right. So now left and right continuity. We define continuity above. Left and right continuity has less conditions on it than the previous definition. First is what we call left continuity at a point. A function f is said to be continuous from the left if at x equals a, if the limit from the left of f of x equals f of a. Notice that we have the negative sign here. In the previous definition from 1.51, we didn't have that sign, which meant the limit from the left and right had to be the same. Here, we only need the limit from the left to exist. Same with this one. For right continuity, we only need the limit from the right to exist. But they both have to be equal to the function's value there. So let's just see this illustrated. At 2 here, this function is continuous from the left, because as I come in from the left, the limit exists. I'm approaching 8 from the left. And that's also equal to the function's value there, because there's a solid dot. That's going to be 8. So the limit from the left is 8, the function's value at 2 is 8, and since they're equal, it is left continuous there. Here, if I change the graph a little bit and make that point be down here instead, then this would be right continuous at 2. So when I come in from the right, the function is approaching a value of, looks like 5, and then at 2, it's defined to be 5. So let's see if I got this right. Yes. The limit from the right is 5. The function's value at 2 is 5, and therefore is right continuous. Of course, we saw this earlier. It's not generally just continuous at 2, but it's right continuous at 2. Okay, continuity on an interval. A function f is said to be continuous on an interval if it is continuous at every point in the interval. Remember, our definition of continuity was being continuous at a point. Now we're trying to say, hey, look, if at every single point in some interval the function is continuous, then it's continuous on the entire interval. At the left endpoint, the function only needs to be right continuous, and at the right endpoint only needs to be left continuous. So look at this. This function in here, I can draw it without picking up my pencil. Between 1 and 3, I can draw it. And at the endpoint, 1, I am right continuous because I come into this value and it's defined to be that value when I get to 1. So I head towards the function's value there. And then at 3, as I head in from the left side, the left-hand limit exists. And it's left continuous. So I'm right continuous here, I'm left continuous here, and it's nice and continuous on the inside, so it's continuous on the entire interval. This explanation shows it. Here's my right continuity at 1, Here's my left continuity at 3, and of course it's continuous all on the inside just because of the picture. All right. So now, combining continuous functions. Given two functions, f and g, which are both continuous, given two functions, f and g, which are both continuous, and a constant c, and a constant c, and a point x equals a, then we have the following. Okay, sorry, I had to had to pause the video real quick, so let me start this over. This is a theorem about combining continuous functions. If we're given two functions f and g, which are both continuous, and a constant c, and a point x equals a, then we have the following. First of all, if we add or subtract two continuous functions, then we get a continuous function. So the sum of two continuous functions is still continuous. We don't lose continuity by adding two continuous functions together. The second part of the theorem says that if we multiply a continuous function f by a constant, then we still have a continuous function at the end. This next one says that if we take two functions f and g that are both continuous and we multiply them, then we still have continuity at that point x equals a. So the product of two continuous functions is still continuous. And the last one says that the quotient of two continuous functions is still continuous. So all this is telling us is that when we do algebraic manipulations of continuous functions, we still maintain the continuity of those functions. We don't have to worry about losing continuity by doing these algebraic operations. Okay, the next theorem has to do with which functions you can already say are going to be continuous. So this is a nice theorem. First it says every polynomial function that exists out there is continuous on the entire real numbers. So you remember polynomial functions are those smooth ones that look like little roller coasters. You can be guaranteed that every polynomial function is continuous on negative infinity to infinity. Rational functions, those are the ones that have the asymptotes and stuff. These are continuous on their implied domains. So remember, implied domains is where they are defined. Rational functions are nice, they behave well on their domains. Of course, there are certain points that you can't plug in, but everywhere you can plug in, you can be assured the continuity. Every trig function is continuous on its implied domain. Every exponential and logarithmic function is continuous on its implied domain. So here's an example of a polynomial. We can see it's nice and smooth. There's no jumps in the graph. There's no jump discontinuities or no infinite discontinuities. Nothing's happening there. So it is continuous everywhere. A rational function like this, let me take that polynomial out. Of course, we have infinite discontinuities here, but on its domain, that means where the graph is drawn, this is nice and smooth. So we can't plug in, let's say, it looks like -2 here. So -2 is not even in the domain of this function. So if we look anywhere other than -2, it's nice and smooth, and there's no jumps. If we look anywhere between -2 and +2, this is nice and smooth with no jumps. And then if we look past +2, this part's nice and smooth with no jumps. So the implied domain is the important part of this. As long as you're looking on its domain, the rational function should remain continuous. Here's a trig function, sine. I think hopefully that's obvious that the sine function is continuous. No jumps, no infinite parts, no removable discontinuities. Exponential functions, nice and smooth, no jumps, right? This just keeps growing and growing and growing and growing and growing, but the graph exists everywhere. Here's a logarithmic function. You can also see this one. This one is continuous everywhere. Of course, you can't go into the negative values and you can't plug in 0, but down here, this is nice and smooth and continuous. You can't be at 0, but that's okay because 0 is not in the implied domain. So that's what that theorem is saying. Okay, now composition of two functions. Let's say we take two functions, g and f, and we plug g into f. So we're taking this composition, f of g of x. Then what we can say is if g is continuous at a, so that means this function g is continuous at a point a, and f is continuous at whatever the value of g is at a, because remember, this is the part that gets plugged into f. As long as g is continuous at a and f is continuous at g of a, then the composition is continuous at a. So what I did is I put together a couple of compositions here. Here's the sine function, and here's x squared minus x. Of course, sine is continuous everywhere, and x squared minus x is a polynomial. So we have a polynomial which is continuous everywhere, and we have sine which is continuous everywhere. And when you compose the two, you get something that is continuous, and you can tell by the graph it's continuous everywhere. Okay, now let's look at e to the cosine x. Cosine x is continuous everywhere because it's a trig function, and e is continuous everywhere. So when you compose the two, when you put cosine into e, you get a continuous function as the graph shows. Next one. Natural log of x over x squared plus 1. Okay, this is a rational function. The denominator can never be 0. So this is defined everywhere. So it is continuous everywhere. And then the natural log function is also going to be continuous. So you have a continuous function inside of a continuous function. The graph of it is continuous on its implied domain. Then you have this one. The square root function is continuous on its implied domain, and what's in it is a polynomial, and that's continuous everywhere. So you can see that the result is continuous on the implied domain. Then we have the tangent. If you plug sine x into tangent x, you get a continuous function. All right, so that's the composition theorem. Now, the intermediate value theorem. This is an important theorem right here. I will abbreviate the intermediate value theorem IVT. I didn't do that here, so let me do that IVT. Okay, the intermediate value theorem says that suppose f is a continuous function on a closed interval ab, where f of a does not equal f of b. That just means that the value of the function at the two endpoints is not the same. Also, the function was continuous on the entire interval. That means continuous at every point there. Let n be any number between f of a and f of b. Then there exists a number c in the interval ab such that f of c equals n. All right, what the hell is that saying? All right, here's what it's saying. First of all, we have, this is just a continuous function. The theorem, the intermediate value theorem, says we have to have a continuous function on a closed interval. So let me show you that function, but I'm going to close it off, put it on a closed interval. Boom, there it is. Now, I want to make sure that f of b and f of a are not the same. So as you can see, here's f of b. We're up here at 13. F of a, which is -2, is going to come out to be -12. So these two are not the same. So we've got this continuous function on a closed interval. The two endpoints are not the same. Now we want to let n be any number between these two values. So let me pick an n. There's an n. Anywhere in between f of b and f of a. I'm going to choose any value. So here, I'll pick one right there. Boom. Then there exists a number c in the interval ab such that f of c equals n. What the heck is that saying? It's saying that somewhere this value is attained or achieved by the function. The function somewhere must equal 7.8, and that there is some c where it comes from, 4.7. So you can see that if I move my n around, there's always some value somewhere that's going to give me that n. And that's what the intermediate value theorem guarantees us, the existence of this c. All right, here is an example of where the intermediate value theorem would not work. Okay, so does the intermediate value theorem apply to this one? Well, you can see right away that this function is not continuous. Let me try and lock it down on a closed interval. So now it goes from here to here, and then it goes from here to here. I can still try and make sure that f of b and f of a are not the same. That's fine. But now let's try and choose an n. So if I choose n is equal to 7, there is some value over here where the function hits and comes out to be 7. But if I try and pick a value down, boom, right in there, the function never achieves that value. So the intermediate value theorem would not apply in this case. The reason why it wouldn't apply, let me try and make this a little bigger. The reason why it would not apply is there's no c, nothing I can plug into the function to reach 1.8. but it breaks down because this function wasn't continuous to begin with. And that's what you need for the intermediate value theorem. You need continuity on that closed interval to be able to apply that theorem. All right, so use the intermediate value theorem to show this equation has a solution. So I'm going to do this example in class. This is a very important example, and when I do it in class, I'll come back and I'll refer to this to verify that we were able to show the existence of that solution.